All right, so for this particular topic, we're going to start with just defining rotational kinetic energy and then look at some kind of ways in which it's going to be used. So in terms of rotational kinetic energy, we can start by thinking of a point mass that can travel in a circle. So maybe it's like a ball at the end of a string of negligible mass, something along those lines. But it has some sort of mass, it's moving with some sort of tangential velocity, and it has a radius. So I know that this object is going to have kinetic energy because it's moving. So if I just think of the fact that it has linear kinetic energy is 1/2 mv squared. From now on, we're going to refer to this as translational kinetic energy, K-trans. So it's translational, motion in a straight line. So this particle does have straight line motion at every point in time. Energy is a scalar, not a vector, so it doesn't matter that that velocity vector is changing directions. But if it's moving at a constant speed around that circle, then I have constant kinetic energy. So, but if I think about it, if I want to figure out how does this, because it is rotating, how do I relate the linear motion to the rotational motion? Then that linear speed, that tangential speed here is equal to r times omega. So if I substitute in r omega for v, for this point mass, and I distribute that out, I get k is 1/2 m r squared omega squared. And hey, what do you know? I've seen mr squared before. Mr squared would be the rotational inertia of a point mass. So this is a point mass and that's its rotational inertia. So K is going to be 1/2 I omega squared. And this kind of goes along with our relationship between linear and rotational variables, as things aren't really that different. We're just kind of trading out some variables. So instead of having linear momentum, we have rotational momentum. Instead of having a linear speed, we have an angular speed. So this is going to be our definition of rotational kinetic energy. So this would be K rot is rotational kinetic energy. Now, when I'm talking about how much energy an object has, an object that is in pure rotation has only rotational kinetic energy. But I could describe it with a linear equation. That's okay. But I don't have linear and rotational motion in this case. I just have one. So anytime you have an object that's just rotating, you can either describe it in its rotational terms or kind of in a translational. But this translational is much more tricky for like a solid object. So if instead of being a circle, this was like a solid cylinder, like a disc, the moment of inertia would be 1/2 mr squared. So I could plug an I here. So I wouldn't get the exact same relationship here to go back and forth. So this only worked because it was a point mass. Now, when we're looking at this, you can basically treat like this solid cylinder as a collection of point masses. So basically every one of these little point masses would have its own little tiny amount of I. So what I could do is I could basically find the kinetic energy of each of those little individual point masses, and it would have its own 1/2 I omega squared. Now every point on this wheel is going to have the same omega. And then basically if I wanted to find the rotational inertia of the whole thing, I would sum that up and say, oh well, the sum of all these little ki's is going to be the sum of all these little 1/2 i's omega squared. And what happens is, because the 1/2 is a constant and the omega is a constant, we can therefore define this rotational kinetic energy as 1/2 times the sum of all the moments of inertia of each of the little individual pieces times omega squared. And what do you know, if you were to actually do that for a cylinder, if you could do this, and you can do this with calculus and stuff, then what you would find is this II is 1/2 mr squared. So that's the end of the relationship that you would end up getting. So the fact that we can treat a solid object as essentially a collection of point masses is really where this definition of rotational kinetic energy comes from. We're just using the simple version of just a point mass to kind of represent that. So just realize that this derivation was specifically for a point mass. But this final equation is valid all the time. So on its own, rotational kinetic energy isn't that bad because you just need to know some information about mass, radius, and angular velocity. We do see that if you double the rotational inertia, you double the rotational kinetic energy. If you double the angular velocity, you double the rotational kinetic energy. This is still a scalar value because and it can never be negative because omega is going to be the magnitude essentially of the angular velocity, and doesn't matter whether it's positive or negative because it's squared. Rotational inertia is always a scalar positive value, so therefore the rotational kinetic energy is always going to be a scalar value as well. So we have that idea of rotational kinetic energy. So how is this going to get used? So let's say I have that single mass pulley that we've seen so many times, where this guy has some sort of rotational inertia I, and we've got some little hanging mass here. So if I wanted to find acceleration, doing torque is a much faster way to get to acceleration. But a lot of times they're not asking for acceleration. They're maybe saying, hey, what is the speed of this block when it hits the ground? So if this object here has a rotational inertia, then we're going to have to consider the fact that both objects can be moving. So basically at my initial position, when I think of like energy, I'm going to have initial position and a final position. So when the block's initially here and there. If I wanted to draw an energy bar chart for what's going on, then essentially at the start, I'm going to have some potential for potential energy, gravitational potential energy. I can have some translational kinetic energy, and I can now have some rotational kinetic energy, all at the start. So that's my energy at the start. And then work could be done. So we could actually analyze work for situations. And then you could have potential energy, translational kinetic energy, and rotational kinetic energy at position 2. So if we look at this situation, if we assume that this starts at rest, and that this starts with an initial angular velocity of 0, then that means that both of these are 0. But you're going to start off with some amount of gravitational potential energy. So you're going to have gravitational potential energy here based on essentially the height that this block is above the ground. So it is at a height h. So if I assume that the pulley has a frictionless axle, so there's no energy loss to friction, and I assume that the string rotates without slipping, so we have no slipping, then we're going to have no work being done, okay, and we assume no air resistance or things. So we can assume that there's no work being done in most of the situations that we are going to deal with in rotation. And then at the end, when it's here at the bottom, I can assume that there's no gravitational potential energy because our height is going to be 0. But then the block is going to be moving and the pulley is going to be moving. Now, I don't actually know if these are equal or if one's bigger than the other. I'd have to have some amount of information, but I can, for translational, my block has a speed v. And my pulley has some speed omega, has an angular speed omega, so that they're both moving. So if I wanted to write an energy statement for this, I would say that my potential energy at the start is equal to my translational kinetic energy at the end plus my rotational kinetic energy at the end. Now, the pulley itself does actually have potential energy because it is above the ground. But because it maintains its potential energy at the start, we can neglect the potential energy of the pulley. Now, if they were going to have fun and this thing was connected to like an elevator type something and this thing was actually moving, then you could also have translational kinetic energy for the pulley and a change in potential energy. But you're probably not going to see any situations like that. Most of the time, our pulleys are going to be stationary. So then I would do something like here, and I'd have like mgh is equal to 1/2 mv squared plus 1/2 I omega squared. And that I would be the rotational inertia here. Now here's the thing. If I say wanted to find the speed down here at the bottom, which I'm looking for, and I don't know anything about omega, I can actually still solve this problem even without knowing omega. Because remember that the linear speed here of the string is going to be the same as the tangential velocity of the pulley. And the tangential velocity of that pulley is going to be r omega. So I can say that the linear speed of my block is equal to the linear speed of the string, which is equal to the tangential velocity of the outer rim of the pulley, which is equal to r times omega. So what I can do is I can then use v equals r omega to actually link these two velocities together. And so if I wanted to find linear velocity and I don't know anything about omega, because it's not given to me, I don't know how fast it's rotating, I can say that omega is equal to v over r, and then I can take that and sub in right here. So if I do that, I'm going to end up with mgh is equal to 1/2 mv squared plus 1/2 I times v squared over r squared. Now, there's a lot of times where you know the rotational inertia. In this case, I don't know the rotational inertia. So if I wanted to solve this problem, it's going to look a little messy. But if I kind of group like terms here, I'm going to have mgh equal to 1/2 and then v squared. I can pull a 1/2 v squared out of both terms. And then that would be m plus I over r squared. And then so if I wanted to solve for v squared, I can multiply by 2 and I get 2 mgh is equal to v squared times m plus I over r squared. And then if I divide that over, I get v is going to be the square root, so I'm going to take the square root of 2 mgh over m plus I over r squared. So here's what's really cool about this, is that if I actually have no rotation, then this term essentially is 0 because I'd have no rotational inertia, so I'd have no rotational kinetic energy. And then my speed at the bottom would just be the square root of 2gh, which is what you would get essentially if you just dropped the block. So if this has no rotational inertia, then essentially this block is going to be in free fall and it's going to reach the same speed at the bottom as if I had cut the string and just let it drop. So what's happening though is if I do have rotational inertia, so if I do have rotational inertia so that I have rotational kinetic energy, then what happens is this is going to be a sum, so I'm going to have a larger denominator. So a larger denominator, I'll just do denominator, is going to give me a smaller speed. So the fact that this has rotational inertia tells me that I'm going to have a lower speed at the bottom than if I had just dropped it, which makes sense because I have kinetic energy in both the pulley and the block. So my initial potential energy of the block is being split into the motion of the block and the motion of the pulley itself. So, and then if they actually give you I, so for example, if this was a cylinder and I was equal to 1/2 mr squared, what's going to end up happening is mass can actually cancel out, and actually the radius can cancel out too. So that it would just be dependent on essentially the coefficient that you choose here, and like height is basically all it would depend on. But you'll be able to see that when you start practicing. So the other weird and wonky problems that you're going to see have to do with like those elongated bars. So we've seen these already last unit. And so for example, if I have a long thin rod that can be pivoted about this axis right here so that it can like swing, then what's going to happen is as it swings, it's going to change energies. So it's going to have some potential energy at the start and it's going to have some rotational energy here at the bottom. So, and then it's going to continue through and it's going to keep swinging. But how do I handle this? Like, how do I handle energy for an elongated object like this? Because if I look at, say, this point at the end of the rod, that point's going to start off at, say, some sort of h above the lowest point. If I assume this is like h equals 0, it's going to be at some sort of h here, and it's going to go all the way down to this point. If I look at the point right here, as it rotates, there's actually no change in potential energy. If I look at a point in the middle, then that point in the middle is going to have this amount of potential energy. Okay, so it's going to go through that change of potential energy. So which point do you choose? Well, the answer is you always assume that the potential energy is at the center of mass. So we analyze potential from the center of mass of an elongated object, which means I would look at the center here if it's uniform. Now, if this was not uniform and maybe it was thinner over here and thicker here or denser over on this side, the center of mass may not be the center of the object, but they'd have to tell you that in AP Physics 1. They'd have to say, oh, the center of mass is at this length. So most of the time, though, it's going to be a uniform rod, and so you're going to have your energy based off of what happens to the center of mass. And that's really cool because basically if you broke this up into an infinitesimally small number of pieces, and you looked at the change of potential energy for each infinitesimally small piece and added that all up, it's the exact same value you would get as if you treated all of your mass as being at the center of the rod. So if I was to do a problem like this, this is a situation where I have pure rotation. So when I have pure rotation, in this case, and I look at an energy chart, I can have UG1 and I can have K rot 1, but there's not going to be any translational energy in this point. And I can have UG2 and K rot 2. Now, I can assume that my work is 0 as long as this axle is frictionless, and I include the rod in my system so that gravity contributes to potential energy, not work. So I'm going to start off with some potential energy here with my center of mass at a height of h. And if I don't know where the ground is, if they don't tell me where the ground is, I usually just set u equals 0 and h equals 0 to be the lowest point that the center of mass can go. So that's really important. So you wouldn't necessarily select the ground here as a height of 0 because that doesn't make sense for the center of mass. And then I'd have no rotational kinetic energy at the start. You can see if I was somewhere in the middle, then I would have both a height and a kinetic energy, so I'd have potential and kinetic energy. But here at the bottom, I would have no potential energy then because my center of mass is as low as it can go. So then I'd have an equal amount of rotational kinetic energy. So in this case, I'd have mgh is equal to 1/2 of I omega squared. Now this is, if this is a long thin rod about its end, that I would be 1/12 ml squared. If I assume that the center of mass is at the center, then h is going to be L over 2. I'm going to get 1/2. So I'm going to mg L over 2, 1/2, 1/12 ml squared. You'll notice that mass cancels out. And actually this half will cancel that half. One of these L's is going to cancel. And you'll get that, oh, that's my omega squared. So you'll get that G is equal to 1/12 omega squared. Oh, forgot an L. L omega squared. So then if I solve for omega, omega is going to be the square root of 12g over L. So you can see that if this rod was longer, then I would end up with a smaller angular speed. That's what you would get. So those give you some examples of both energy when you have both rotational and translational kinetic energy. We're going to look at it rolling on a ramp in the next video, which is another example where there's both translational and rotational kinetic energy.